This is lecture 3 for week 8 of CS 1030. In the previous lecture segment, we talked about digitizing sound, and in this one we'll talk about digitizing images. So the way we represent an image is a collection of pixels. A pixel is a picture element, that's what it stands for. And a pixel is a square, or sometimes rectangle, part of an image that's each pixel is always completely the same color. And so then the way that we represent an image is to make a two-dimensional array of pixels, and that shows us that represents the image. And we often talk about an image in terms of its resolution, which is the number of pixels that comprise it. And so, for example, we might have an image that's 2,000 pixels wide and 1,000 pixels high. And so that's how we describe this image. It's 2,000 by 1,000 pixel image. So let's talk about black and white or grayscale images. One way to do this would be to represent each pixel using an intensity between 0 and 255. And in this kind of a scheme, the intensity 0 would mean that no light is emitted by that part of the screen, or by the part of the screen representing that pixel. So that that pixel would be completely black. And 255 would correspond to that part of the screen emitting as much light as it can. So it would be white, and so it would be white. And so one question we can ask is, how many bits do we need to describe a pixel in this kind of a grayscale image? And of course, it's 8 bits because 2 to the 8th is 256, and the numbers from 0 to 255 have 256 different possibilities, so those are exactly represented by 8 bits, or 1 byte. And one thing we can ask ourselves is, what would we do if we had fewer bits per pixel? So for example, what would happen if we had only 1 bit per pixel? And the answer is, we would just try to do the best we can with less information per pixel. So if there's 1 bit per pixel, as we know, a bit is either on or off, so this pixel would either be completely black or completely white. And then the image, of course, wouldn't look very good, but we can sort of do whatever we want here. And so one thing I want to talk about is how when we take an analog signal in the real world and we digitize it to make an image, there's going to be some quantization. There's going to be quantization going on. So for example, if the brightness at a particular pixel sensed by a camera is 57, we might represent that if we have 4 bits per pixel using 1011. And then when we go to show the image on a screen, that's going to correspond to a quantized value of 53.7. And in this lecture segment, I'm not going to talk about how we arrive at that exact number. We'll talk about that in the next lecture segment in number 4 for week 8. But the point that I'm trying to make here is that when we quantize images, or when we quantize brightness levels in the real world to represent them as an image that's represented in a computer, there's going to be error. We're never, just like as we saw in the sound in the previous lecture, we're never going to completely accurately represent something from the world. And again, we'll talk about how this actually works in the next lecture segment. So now let's talk about color. So color is a complicated topic, and there's a lot of different ways that computer images store color. But what we're going to talk about here is one of the simpler and more common ways to do this. So in this scheme, we represent the color of each pixel using 3 color channels. And again, there's variation here in what those color channels are, but a common choice is to have a red channel, a green channel, and a blue channel. And the reason we might make those choices are that those 3 colors are a reasonable match for the kinds of cells that are in our eyes that perceive colored light. And so let's talk a second about how the eye works. So the way the eye works is there's 2 kinds of cells that sense light. There are rods, which sense only the intensity of the incoming light. So rods allow us to see in black and white, and rods are very sensitive. And so one thing you might notice is that in an extremely low light, that is to say, if you're out at night and there's no moon, it's almost dark, you basically see completely in black and white because there's only enough light to stimulate the rods in your eyes. When there's more light, for example, during daytime, not only do the rods work, but also the cones in your eyes work. And the cones are the cells that can see color. And the way that works is there are 3 different kinds of cone cells, and those are shown here. There's the S, M, and L cells, and they respond proportionally to different wavelengths. So for example, the S kind of cone cell is going to respond maximally to something like 450 nanometer light, and almost not at all to 700 nanometer light. And the M and L cells will respond a little bit differently. And you can see that there's quite a bit of overlap between these 2 kinds of cone cells. And that's sort of weird, but that's just sort of, that's how it works. Okay, so we're going to represent a pixel as a collection of 3 different intensities in 3 different color channels. And so one way we might do that is to represent each of the brightness of each of the 3 channels using a number in the range 0 to 255. So that would be then, of course, using 1 byte per color channel, because that gives 256 different possibilities. And this is an additive color space, meaning that a purely white pixel would be represented by the maximum intensity in all 3 of the color channels. So a white pixel would be represented by 255, 255, 255. A completely red pixel would be represented by 255, 0, 0. And what that means is that that pixel corresponds to emitting the maximum possible amount of red light and no green light and no blue light. So a purely black pixel would be represented by 0, 0, 0. That is to say, we're emitting no light on any of the channels. And a medium gray would be something like 128, 128, 128. And something I'd like you to do, if you don't mind taking a few minutes after you watch this segment, is click on the link shown at the bottom here, which is a color picker that's built into Google's search engine. And what this lets you do is drag around a mouse on a screen, and it changes the color and it shows you the RGB, that is to say the red, green, blue components of a lot of different colors. And so you can sort of gain a little bit better understanding of this by playing around with this for a few minutes. Thanks.